So in the previous question, in the previous lecture, we have discussed the PN junction, forward biasing and the reverse biasing. If you revise, this is the forward characteristics of the diode current in the voltage, and this is what? This is the reverse bias. This is the forward bias characteristics, and this is what? Say reverse bias, right? So now we will see the in this lecture the application of diode. Application of diode. So what is the diode? The PN junction simply the symbol of the diode is this, and the PN junction, unbiased PN junction, is called the diode. So what is the application of this PN junction diode? We have to see. So very good example of this PN junction diode is the half wave rectifier. Half wave rectifier. Half wave rectifier. Right, what is the half wave rectifier? The half wave rectifier is the combination of the diode, right, which convert AC to DC, right? What is the AC? Alternating current. Do you know the alternating current? The alternating current is like this. Are you getting or not? Right, in the half wave rectifier, let's see, the half wave rectifier, we have the one diode, right, and it is connected to the load resistance like this, and we have the AC supply like this. This is the symbol of the transformer, right? This is the symbol of the transformer. Are you getting or not? This is the diode 1, this is the load resistance, and this is the step down transformer or step up. I am considering this is the step down transformer, right? And this is the 220 volt AC is supplied from here, right? This is the 220 volt, and here suppose the less potential is less voltage is the output of this step down transformer, right? So for example, this is the two terminals, right? So the step down, suppose this is the AC supply. The AC supply of the peak voltage is suppose the V0. Are you getting or not? When the step down transformer is applied, right, the output voltage is step down, its amplitude or the peak values reduce. Are you getting or not? So at this point A and B, what is applied? You may consider this is the input wave which is applied at this point, right? So this is the input applied from 0 to T by 2, and this is the T by 2. This is the T, right? This is the 3T by 2. So for half wave it is positive, for half wave it is next half wave it is negative. Are you getting or not? Yes. You tell me, if you consider the first half wave when it is positive and it is negative, for first half wave, for first half cycle, first half cycle, right, D1 is forward bias. Forward bias. Do you understand or not? Why? It is positive and it is negative. So if it is forward bias, so what will you have? In the forward bias, the diode act as a wire, and this is the load resistance. So whatever the input is applied over here, the same output is obtained across the resistance. So if this is the input voltage and this is the output voltage across the resistance, so whatever the input voltage is equal to the output voltage is equal to the input voltage for first half cycle, you can say. So the same voltage is obtained, right? In this case, for the first half cycle, the diode is on, right, and the output voltage is equal to the input voltage. Do you understand this thing or not? Right, Sanjay? Hello? Right. For the next half cycle, you tell. For the next half cycle, what is the next half cycle, you tell? It is the negative. Are you getting? It is negative. So for next half cycle, it is what? it is negative and it is positive. When it is negative and it is positive, for next half cycle, diode D1 is reverse bias, is reverse bias. Are you getting or not? If it is reverse bias, so what will happen? The diagram will be, the diode is off. Diode is off. If the diode is off, it acts like this. So no current flows. So what is the output voltage across the load resistance? If this is the load resistance, the output voltage is 0. For the next half cycle, what is the output voltage you tell? Say 0. Right? For the next half cycle, if it is positive, so again here the diode is off. For the next half cycle, it is positive, diode is on, and all the input voltage is equal to the output voltage, then it is again 0. Are you getting or not, you tell? Right? So that is why it is called the half wave rectifier. Half wave mean, if this is the input voltage, this is the input voltage, this is the input voltage. So in the output voltage over here, this is the output voltage, you will get the half wave only. The positive half wave you will get as it is, but the negative half wave is clipped off, right? It is not present in the output. Again the positive wave is present as it is, and the next half cycle is absent, or it is clipped off. So therefore it is called the half wave rectifier. Half wave rectifier means it passes the positive half wave, right? The output is obtained for the positive half wave, but for negative half wave the output is 0. Do you understand this thing or not? Copy this. Right? Okay, wait for 1 minute. Wait for 1 minute. Okay, so this is the half wave rectifier. And what about the full wave rectifier? In the full wave rectifier, what we have? In the full wave rectifier, we use the two diodes. The second is the full wave rectifier. In the full wave rectifier, we have the two diodes like this, right? There are two diodes and this is connected to the center tape transformer. This is the input or the primary coil of the transformer. These two lines represent the core of the transformer, and this is the secondary coil of the transformer. Are you getting or not? So listen one thing, this is the two diode D1 and this is the D2, right? And this is the resistance, right? This is the output resistance, and this is terminal is connected to this point. Are you getting or not, you tell? Right? So this is the condition of the full wave. This is the full wave rectifier, and the output current is taken, output voltage is taken across this. Are you getting or not? So let's see how does it work. For the positive half cycle, like this, right? And if it is the input voltage and this is the output voltage, right? This side 0 to t by 2 to t, it is equal to 3t by 2, right? Time axis 0 to t by 2 to t to 3t by 2, and this is the time axis. Are you getting or not? Right? Right. So for first half cycle, this is the center tape transformer. Listen one thing, this is the terminal, right? This is assumed to be the 0 for first half cycle. For first half cycle, you tell. For the first half cycle, it is the positive, this is the positive, this is the negative, and this is the 0. So you tell me, for first half cycle, D1 is forward wise and D2 is reverse biased. Reverse biased. Do you understand or not? So D1 is on and D2 is off. What is the circuit? Then this is the D1. The ideal diode act as a wire, and this is the load resistance, and this is the off. Right? It is off. D1 is on, this is on, and this is off. So in this case, this is the plus, this is the 0, this is the minus. So current flows in this direction. So this is plus minus. So the load, if this is the load resistance, the output voltage is obtained in this way. So the output current or the output voltage, you can assume like this. In this case, this is the output voltage. D1 is on, D2 is off. Are you getting this thing? Yes. Copy this first. Right? Okay. For second half cycle, yes, you tell me. For the second half cycle, so it is negative, it means it become negative, and it become positive, it becomes 0. So diode D1 is reverse bias, right? And D2 is what? Forward bias. Are you getting or not? So there, if it is reverse bias, D1 is off and D2 is on. Do you understand this thing or not? So how the current will flow? This is the D2 diode and this is the load resistance. Right? This is the load resistance. So in this case, it is plus, it is 0, right? And this resistance is D2 and this resistance is D. This diode is D1. This is off, this is on, and the current flows in this way. Again, listen one thing. The current is again in this resistance flowing from left to right. Are you getting or not? So what does it mean? The potential, output potential across this is again in the same direction. Is it correct or not? So therefore the negative half cycle is like this. So the output voltage is in the same direction, the current flows in the same direction, the unidirection current is over there. So this is the conversion from AC to DC, right? DC means the current remains in the same direction, but here D1 is off and D2 is on. Are you getting or not? Again, when for the next half cycle, right, for the next half cycle, this thing occur, it become positive, it become negative, and it becomes 0. Again, the current in the resistance, load resistance flowing in the same direction, but here D1 is on and D2 is off. So this is the, in this case, the whole wave, this is the input voltage wave supplied, this is the output voltage. So all the potential is getting, we are getting the complete wave, which is right, and the current is flowing in the same direction. Is it clear or not? Copy this. Right? If you consider, okay, if its frequency is what? Its frequency is, suppose the 50 Hertz, its frequency is what? Its frequency is 100 Hertz. Are you getting or not? Why? Because this is the periodic function, the time period is T, This is also the periodic function, the time period is t by 2. If the time period is half, the frequency become double. Do you understand or not? Right? Listen, one more thing. Can I clear this? Right. In the output, listen one thing. If you consider the electrical equipment at your home, like your mobile, radio, your TV, right? DC supply is necessary, is required. What is the DC supply? You tell. DC supply mean the voltage is constant as a function of time t. But if you consider only the rectifier, what the output voltage you are getting, like this. This is the output. Although it is in the same direction, but it is 0, then maximum, 0, then maximum, 0, and then maximum. So this is the ripple, right? And which is not very good power supply, assumed to be very good power supply. To reduce this ripple or to remove this ripple, what we have, what we do, can you tell me? Yes, we will use a capacitor across this power supply, right? So what, the after applying the capacitor in parallel with this power supply, right, this type of the, right, the power supply we are getting, right, like this. So if you increase the value of the capacitance, so the ripple is small as compared to this, right, like this, like this, like this. So after applying the good capacitor, you will get approximately the straight line. So this is the good power supply where the voltage is constant, which is essential for the driving the different type of the instruments. Is it clear or not? Copy this. Wait for 1 minute. And what is the, listen one thing. Okay, listen one thing. For the full wave and half wave rectifier, for this is the input voltage. This is the input voltage. Are you getting or not? This is the input voltage. So for the input voltage, what is the average current? Say 0. This is the, because it is positive, negative, positive, negative. Are you getting or not? What is the half wave rectifier output? Half wave rectifier. Half wave rectifier. The output is what? Say like this, right, like this. This is the 0, like this, this 0. Are you getting or not? 0 to t, like this. So only the positive wave is obtained as a function of output. So in this case, for the half wave rectifier, the RMS value if you want to find, so it is I naught by 2, or you, if you assume this is the voltage, right, so the output voltage is what? This is the output voltage. So if this is the peak value V naught of the voltage, right, what is the voltage? Input voltage supply is V naught sin omega t. This is the alternating voltage, and this is the DC voltage, right, half wave rectifier of the VRMS is V naught by 2, and V average, if you want to find, this is V naught by pi, right. Now if you consider the full wave rectifier like this, right, for the full wave rectifier, if you want to find the RMS for full wave rectifier, 0, t by 2, t, 3t by 2, 2t. The VRMS is what? V naught by root 2. The V average is equal to what? 2 V naught by pi. Is it clear? So this value for the half wave rectifier and this value for the full wave rectifier, you have to remember. All right. copy this. So now we can have the next topic, and this is the Zener diode, right? Zener diode. Zener diode. What is the Zener diode? Right. This is the highly doped PN junction. Highly doped PN junction. Are you getting or not? Listen one thing. जो conventional diode, the conventional diode are lightly doped. Lightly doped. Do you understand or not? This is the conventional diode in which the current flows only in this direction. Are you getting or not? The current does not flow in this direction. The current does not flow. That is why its symbol is what? This arrow symbol is what? It is the arrow. Arrow means the current can flow in the one direction. This is the unidirectional device. Unidirectional. Are you getting or not? And this is the barrier. The line represents that the current does not. It produces the obstacle in the path of the current. It flows from N side to P side like this. Are you getting? This is the conventional diode, and the doping is lightly. Lightly doping means the impurity atoms are less number as compared to the highly doped PN junction. If in this PN junction, if the semiconductor is highly doped means if we increase the concentration of the impurity, then what happens? Listen one thing. In the conventional diode, if suppose this is the P and this is N, this is the negative, and this is the depletion region, right? If doping is high, so this is the depletion region. The depletion region is very small, right? The doping is high mean the negative ion, positive ion are more as compared to the conventional diode. This is conventional, right? And this is highly doped. What is the reason between this conventional diode and the highly doped diode? Although the symbol of this conventional diode is this, and highly doped PN junction is called the Zener diode, and the symbol of Zener diode is like this, right? This is the symbol of the Zener diode. What is the difference between this diode and this diode? The difference is of the characteristic. First copy this, whatever you want to do. So what is the difference, basic difference between the conventional diode and highly doped? If you make the graph, the reverse bias characteristics. So in the reverse bias characteristics, right, this is the breakdown of the voltage, right? This is the breakdown of the voltage. Are you getting or not? In this case, the diode is damaged, right? But the highly doped PN junction, which is called the Zener diode, are especially doping is done such that the breakdown occurs in the conventional diode. The very high current flow, and due to this the heat is developed and the diode is damaged and it is useless. But highly doped Zener diode, right, the breakdown occur very soon. Before breakdown, right, before this breakdown, this is called the avalanche breakdown in case of conventional diode. In case of Zener diode, the Zener breakdown occur. Right? And this is the Zener voltage, which is very less as compared to the breakdown voltage of the conventional diode. For example, the Zener diode may be the 12 volt, or it may be the 5 volt like this. But the high current, the Zener current IZ, right, is flowing but diode does not. Diode does not damage. Does not damage. Right. So this diode work in the reverse bias right, in the reverse biasing it is acted. Are you getting or not? And its Zener breakdown voltage is suppose the VZ, which is fixed. Are you getting or not? So this is the basic difference between the highly doped PN junction and the conventional doped PN junction. The breakdown occur at very high voltage, the breakdown occur very soon, and this voltage across the Zener diode remains constant, and the Zener current, the current flows over here. The current may be the any value. This is the IZ1, it may be the IZ2, but the voltage remains approximately what? Constant. This current, Zener current, IZ current, may be any value, maybe any value, but potential difference across Zener diode, Zener diode remain constant. Zener diode remains constant, right? Remains constant. Are you getting or not? Copy this. So this application of this Zener diode, application. Can you tell me what is the application of Zener diode? Yes, it is used as a voltage regulator. Voltage regulator, right? How it is used as a voltage regulator? This question is only the question which comes on the Zener diode, right? The important point is that the Zener diode work in the reverse bias condition, and it is used as a voltage regulator. What is the circuit of the voltage regulator? Suppose this is the Zener diode applied, right, and the Zener breakdown voltage is VZ over here, and this is equal to suppose the 5 volt. Are you getting or not? This is the resistance, right? This is the another resistance, and this is the battery, right? Like this. Suppose this is the 20 volt, and the Zener voltage is given as the 5 volt. Are you getting? This is 10 ohm, and this is the 20 ohm. Is it clear or not? You tell. So if you find the potential, this is the output voltage. The output voltage across the Zener diode voltage will be always 5 volt. Whatever the voltage, whether you apply the 15 volt, whether you apply the 25 volt, whether you apply the 20 volt, are you getting or not? Whether you apply the 19 volt, the output voltage is always 5 volt. Are you getting? If you consider your charger, mobile charger, so what is the voltage of your mobile charger? Output voltage. It provides the 5 volt DC. Do you understand this thing or not? Your mobile charger is always provide 5 volt DC, right? So if this is the 19 volt or the 20 volt, suppose it is 20 volt, if it is 5 volt, so the voltage across this resistance will also what? Say 5 volt. Is it clear or not? It is fixed. Why it is fixed? Because the Zener breakdown voltage is what? It is fixed. It is 5 volt. It cannot change whatever the value we are applying. Also it is in reverse direction. So you tell me what is the current flowing over here in this I1. I1 is V upon R. What is the potential difference? Equal to the Zener voltage 20. You choose this the 20 kilo ohm, 10 kilo ohm, and it is the 20 kilo ohm, right? 10 ki power 3, 1 by 4 milliampere, 0.25 milliampere is the current in this resistance. Are you getting or not? You may assume this is the I2. So this current is I2. Are you getting, Sanjay? Can you find this current I1 in the resistance, and what is the current, the IZ? right? Also find current through this resistance I1 and the current through the Zener diode. Copy this. So let's see the potential drop. Suppose it is the 20 volt battery, right? This is the resistance, this is the another resistance. So it is the 5 volt, right? So what is the potential difference across this resistance? Say 15 volt. So can you find the current in this resistance? The resistance is say 10 kilo ohm. Are you getting? So what is the I1? Say V upon half. So what is the V? V is the 15 volt. The resistance is 10 kilo ohm. So this is 1.5 milliampere is the I1 current. Do you understand or not? And if this is the 20 kilo ohm, are you getting or not? So what is the I2? And this is the I2. So I2 I have found it is 0.25 milliampere. Is it clear or not? You tell, Sanjay. So therefore, what is the reverse bias current here? The Zener diode current is what? You tell. So I1 is equal to I2 plus IZ. So the IZ is what? Say I1 minus I2. So what is the I1? I1 is 1.5 milliampere. What is I2? 0.25 milliampere. So this is 1.25 milliampere is the IZ. Is it clear or not? You tell. So what is the Zener diode current? Zener diode current is 1.25 milliampere. Is it clear, Sanjay, or not? You tell. It is not the same. So listen one more thing. If you apply the 15 volt in place of 20 volt, the output voltage will remains always 5 volt. Only the current I1 and IZ may change. Do you understand or not? Copy this first. So in this example, listen one thing. This resistance is assumed to be the load resistance, right? In some book, the figure is given like this. Or listen one thing. If this is the suppose this is the load resistance, and from somewhere suppose this is the power supply, right? And this power supply is fluctuating. So if you want to take the output voltage, so if the input power supply is fluctuating, the fluctuated output voltage you will get. To fix this voltage, we will add a Zener diode. So this is the Zener diode. Are you getting or not? You tell. In this case, what is the Zener voltage? In this case, the Zener voltage is 6 volt. Then this is the load resistance is given as the 1000 ohm. Are you getting or not? This is the output voltage. So the load resistance is of 1000 ohm, right? And this is the Zener voltage. Vz is equal to 6 volt. Are you getting or not? And this is connected with a series resistance. This is the resistance. What is that? Is 100 ohm. Are you getting, Sanjay? And this is the EMF, is the 9 volt power supply. So this is the figure only. This is only and only one figure in all the book and all the illustration. How the Zener diode voltage act as a voltage regulator. Whatever the input supply you will give, if this is the Zener diode, the 6 volt, right? The output voltage always will be the 6 volt. Do you understand this thing or not? You tell, Sanjay. Right. Copy this first. So now, if this is the 6 volt, so the 6 volt is over there. Can you find the load resistance current? Yes, Sanjay. What is the potential difference across this? Say 6 volt. So IL is equal to Vz upon R load. The Zener diode voltage is equal to the load resistance voltage. This is 6 upon 1000 is equal to 6 milliampere. Is it clear or not? If this is the 6, if this is the 9, what is the potential difference across this? You tell. 3 volt. Very good. So now the current through this series resistance Is is equal to Vs upon this is the series voltage divided by Rs. What is the Vs? Say 3. And what is the resistance? Say 100. Are you getting or not? So this is 30 milliampere. Are you getting? So if this is 30 milliampere, what is the IZ? We apply the KCL. The IS is equal to IZ plus IL. The series resistance is 30 milliampere. This is the IZ plus IL is what? 6. So IZ is 30 minus 6, 24 milliampere. Is it clear or not? You tell. Right? So this is the Zener diode current. If we change the 9 volt to 12 volt, everything will be same for the load resistance, right? But the Zener current and this current will be changed, but the output voltage will remain same, and the current in the load resistance is always same, because the Zener diode is fixed, Zener voltage is fixed, the load resistance is constant. So this current will not change even there is a fluctuation in this voltage, even it is 9.1 volt or 9.5 volt or it is 8.5 volt. So if this input voltage is fluctuated by due to some reason, the current in the load resistance does not change because of this Zener diode, and therefore that is the fixed voltage across this. So this is the application of the Zener diode, right? As a voltage regulator, you have to remember. Are you getting or not? All the devices like your mobile charger or where the constant DC supplies is needed, so this Zener diode is always connected in parallel with the load resistance like this, right? So this is the application of the Zener diode. Copy this. This is the Zener diode, right? Like this. This is the Zener diode. Breakdown voltage is what? 9.1 volt. The maximum power, the current is IZ. What is the power? Say I square into R or V square upon V square upon R, or P is equal to V into I. So Vz into Iz. What is the maximum power? The maximum power is 364 milliwatt, right, is equal to Zener diode voltage is 9.1 into the maximum current they are asking. So this is the simple thing. So what is the maximum current? 364 into 10 to the power minus 3 upon 9.1. If you divide this, then we can find the answer. So this is a very good question for the half wave rectifier. Here this is the diode and this is the resistance. Now the input signal over here, it is shown in the figure. This is the 0 volt and this is the plus 5 volt and this is the minus 5 volt, like this, right? This is the minus 5 volt. So when it is so what we have to find, listen one thing, the square input signal is like this. This is the minus 5 volt, although this is the signal. This is the plus 5 volt, plus 5 volt. This is the minus 5, the minus 5. Are you getting or not? So what is the output voltage across this load resistance? You have to tell. So you tell. This is the half wave rectifier. Only the positive half cycle is if this is the input voltage, right? This is the input voltage. So in the output voltage waveform, what will you get? Only the above, right? The positive half cycle you will get. Is it clear or not, Sanjay? The positive half cycle, plus 5 0, plus 5 0. So what the output you will write? Which is the correct output? Say 1 0 plus 5, right? This is the half wave rectifier, right? So only the positive half cycle you will get as a output, and the negative cycle is clipped off due to the diode property or diode reverse bias condition, right? Copy this. Can you read the next question now? Okay. Okay, so I think you better understand in this way. This is the diode. Always with the Zener diode, you will get this circuit. It is a voltage regulator. The Zener voltage is 6 volt. This is 1 kilo ohm, right? this is the series resistance, and this is the battery of the 18 volt, right? So what they are asking, the current I, this current I they are asking. So what is this current you tell? I load resistance 6 upon 1 kilo ohm, right? 6 milliampere. Are you getting or not? If this is 6 milliampere, this is the 6 volt, this is the 18 volt. What is the potential difference across this? Say 12 volt. So if you want to find this current, so I is equal to what? V upon R. V is 12, R is 500, right? So I is 12 into 1000. 12 upon 5 into 10 to the power minus 2. 2.4 into 10 to the power minus 2. 0.24 milliampere is this current. So they are not asking the load current, they are not asking the Z current, they are asking only this current. So 0.24 milliampere is the correct answer. Wait for 1 minute. 2.4, right? 24 milliampere is the correct answer, right?